Efficient coding, alternative approaches. Let's recall that we have formulated the efficient coding principle as to find an optimal transform K that transforms the input signal S to an output O, and this optimal K should be such that it minimizes this objective function, namely to minimize a neural cost of the coding while maximizing the information extracted by the output O about input S. If this neural cost is chosen as this output variance or total output power, then this is the form of this objective function. If we in addition also approximately treat this signal S and the input noise as Gaussian, and also treat this K approximately as linear. This is a simplification or approximation of the early resistive fields. Then we can find an analytical solution for this K that minimizes this objective function. And this solution we have shown to have these three conceptual stages. And this solution provides lots of insights and predictions about visual resistive fields in early visual stages, particularly for retinal coding. We have also shown that in this analytical solution, there is a freedom in choosing the third stage, the multiplexing matrix U. Accordingly, neural resistive fields in the retina and those in V1 could be seen as arising from different forms of this matrix U. However, we have seen that this solution is not able to explain why V1 has a vastly overcomplete representation. Therefore, one could ask if there are alternative formulations of this efficient coding principle or ways to avoid some of these approximations to provide a better understanding. This Gaussian approximation here can be avoided if we obtain K by numerical solution rather than by analytical solution. And to do that, you start with a value K and then you change it according to gradient descent. You change it according to this value, the derivative of this objective function as a function of K. And you change one step at a time until you reach a K value that makes this objective EK minimum. For example, this is what Bell and Snosky did. They simplified it by the following steps. First, they assume that there is little noise in the images. Second, they fix the neural cost term here by fixing the dynamic range for the output O. Then minimizing this objective becomes just maximizing the mutual information, and therefore it is just maximizing the entropy for O when the dynamic range is fixed. Now, taking O as a pointwise monotonic function of the linear transform of S with a fixed dynamic range, for example, taking this sigmoid function, then you can show that this gradient descent follows this formula to obtain the efficient transform K. This is an average of this derivative over the ensemble of visual inputs. In practice, it was done by doing this derivative-based adjustment of K over visual image samples as a stochastic gradient descent. So, in this process, it's done by sampling over images of 12 by 12 pixels. And the resulting K gives the V1-like resistive fields. However, now because of these images of finite size, the statistical property of translation and scale invariance in natural scenes is not captured very well. And also the simulation makes this approach lacking predictive power. For example, it's difficult to understand how noise or the statistical properties of visual images should influence the resistive fields. Meanwhile, this approach also could not explain why V1 has an overcomplete representation. Another example is called sparse coding. In this approach, the neural cost is a function, SPOI, yeah, and it defines a cost of non-sparseness. So when we have a population of neurons O, if the number of activated neurons is small, and then the representation of visual input is said to be sparse. So if you have typical inputs, you have fewer neurons active, then it's called sparse representation. So therefore, for each OI, this sparseness cost should increase with the value of OI or typical values of OI. And we may say that such a function, quadratic function of OI ensemble average, also belongs to such a kind. However, often in these sparse coding approaches, a typical sparseness function is this one. And it has been argued that such a cost function encourages the output OI to be non-Gaussian distributed. The second term in the objective function to maximize the extracted information is now replaced by something qualitatively similar, namely to minimize the reconstruction error. When we take reconstructed signal as S-prime from this output O, it's natural to expect that when this output O can extract more information about S, then this S-prime should more resemble the original signal S. Yeah, so they are related, so that this reconstruction error is smaller. Therefore, the objective function is this one, taking this sparseness term and the reconstruction error. And the optimal transformation K is then obtained through numerical simulations, again using noiseless images of 12 by 12 pixels. So noise-free is again assumed to make it easier. And this approach also then leads to V1-like resistive fields. And it still remains so that it cannot explain why V1 should have an overcomplete representation, or exactly how overcomplete it should be to make this sparse coding. And the next two issues also still remain. So numerical simulations using natural images, which are sampled directly from the true probability distribution, can help us avoid making Gaussian approximations or assumptions about the true probability for this signal S. And this way, all the higher order statistics in the natural images can be allowed to play their role for making the coding efficient. And it's encouraging that such an approach gives the V1-like resistive fields, although this approach also brings these disadvantages.